Hi, I'm Nick.
And I'm Carver.
And today we have a very special guest. Say hi to Lord Kelvin.
Hi, Nicholas.
Hi, Lord Kelvin.
So this lovely man is not only responsible for creating the temperature scale that we use in physics and chemistry, but also the inventor of an amazing electrical device, the Kelvin water dropper.
This magical device consists of two sets of electrically connected cans, as well as a stream of water coming from the same electrically connected basin. To measure the electricity, you also need to form a spark gap. You see, initially, there will be a charge asymmetry, ever so slight, due to cosmic rays and natural radioactivity, and other things. Assume that one can is ever so slightly negatively charged, while the other is slightly more positively charged. The water in the nozzle responds to this difference in the top cans, letting positive drops fall through the more negatively charged can, and negative drops fall through the more positively charged can. When negatively charged particles attracted by the positive ring fall into the bucket, it gives both the bucket and the attached ring on the opposite side a negative charge. This begins a positive feedback loop. The charge continues growing, and the same occurs in the positive set of buckets, but with positive particles. The higher the charge, the more effective the electrostatic induction is, so the charge grows exponentially with time.
To construct a Kelvin water dropper, you're going to need the following materials. First, you're going to need a stand. We built our stand out of wood, but you can use PVC or any other material capable of bearing a large weight. Next, you're going to need two conductive reservoirs. The water is going to fall into these buckets, and they need to be conductive to hold the wire in charge. Next, you're going to need scissors for cutting the wire, a voltmeter to actually measure the charge, wire to carry your charge, string to suspend your canisters that we'll get to later, some type of device that is going to be able to carry water from one place to the next, a lot of energy drinks, both insulative and conductive tape, soup cans that is going to be able to create the charge, a T-coupler that is going to be able to split your stream of water, as well as two insulative blocks to prevent grounding, as well as a lot of patience.
So here's how it should look all put together. First, you need to get this T-coupler all nice and set up so it aligns perfectly with the cans underneath and falls eventually into the bottom buckets. We suggest a coupler with adjustable flow nozzles to allow for different speeds of water flow. Afterwards, ensure that the water doesn't hit the sides of the can, but instead falls directly through the can and into the bottom bucket. The wires should cross so that this can is attached to this bucket, and this can is attached to this bucket. At no time should the two sets of buckets touch each other. To measure the voltage, we used a spark gap. It's a little hard to see, but on a white background you see these two wires. It has a multi-purpose feature. If we connect a voltmeter, we can see what kind of voltage is being put out. If we don't and we get the distance just right, we may be able to see actual sparks of electricity fly across. One more thing. Just make sure, for functionality purpose, and ensure that grounding doesn't happen, that these reservoir buckets sit on top of insulators, otherwise the charge just falls through to the ground.
Let's see this baby in action. So it's very important that when the water streams enter the top of the can, that it is a single continuous stream and there is no disjointed particles. Whereas when it leaves the bottom of the can, there should be turbulence and single droplets should be coming out. So there's three ways to monitor if your device is actually working.
Okay, so the first way you can tell if electricity is being generated is if the drops spread out. As the charge increases in this positive feedback loop, the different water particles repel each other much more, and you see like kind of a further spread out of the spray. I'm getting wet right now, so it must be working.
The second way is to actually calculate the charge using a voltmeter.
The third way is by monitoring sparks across a spark gap. Now watch.
Let's see if we can get it to spark. They've been running for quite a while right now, so we're just going to see if we can get them a bit closer, if we can get a spark. Oh, there it is. But nothing happening now, so let's just wait a bit longer. Nope. Oh,
Nope,
there
there
is
it is.
one. You just wait. Oh, there's one again.
Oh, nice. Hope you're catching all these. So about that second test. We thought we were doing well, but it turns out we're only making around 28 volts.
But Lord Kelvin said we could get about 15,000 volts.
Well, he is a lord, and we are just amateurs. There's a lot of things we probably could have done better. For example, we really needed to even out the space between the can and the water dropper and the can and the bucket. This would have evened out the charge and made the system more effective.
Also, we were wondering if we would have reduced the distance between the water droplets and the actual cans. That may have been able to amplify the charge within the cans, and therefore producing larger charges in the reservoir and seeing larger sparks.
Finally, as it turns out, every time a water droplet hits one of the ring cans, the overall voltage drops, and aiming those things was incredibly difficult for us. But one day we might get it down. For now, we're pretty happy with 28 volts. I encourage you to try it. It was an awesome project. We made electricity, and it turns out just like hydroelectrics work, where potential energy of water creates electricity. Go home, try it, make your own generator, power a lamp or something. It's up to you. Have a good day.